Yeah, we can start the second section in the morning. So Yanyan, we'll talk about Higgs 2ZZ, Standard Model 1, and anomalous coupling measurement.
Okay, thanks to the organizers for inviting me to give this talk. Let's see, so I would like to apologize in advance that given the topic that it's on Higgs 2ZZ, and you know that in the CEPC the main production is ZH, so it's not really particularly on the Higgs 2ZZ decay. So you will see a little bit repetition of some of the highlights, especially on the standard model measurements that I will summarize. And the focus of my talk, I will go through a bit more detail on the anomalous coupling measurements in this case. All right, so let me start with this big picture. So I think the general understanding is that the CEPC or other E plus E minus colliders have a magnitude of 1 to 2 improvement in terms of the cross sections, the couplings, etc. And you can see that the major improvement is on the Z side. And this is why the Higgs to ZZ interactions is really important. As you'll see later that the driving factors for this. So let me just remind you again the main productions of the Higgs boson at the E plus E minus colliders. So as you can see that, for example, at the central energy of 240 GeV, assuming Higgs mass 125, of course, you have 3 productions, but you can see the relative size is really getting reduced quite a lot. So it's quite different picture as we've used to in the LHC. I wanted to highlight over here. So, for example, when we look at these channels, it's not anymore just looking at Z decaying into 2 muons and tagging stuff, as I've learned that, in fact, because the clean environment of the CEPC, all of the decay channels are contributing especially for the cross-section measurements. For the Higgs mass, of course, is a different matter. So the cross-section over here is about 200 femtobond. Just as a comparison, you can see that to study fully the Higgs 2ZZ at the LHC, or high luminosity LHC, the main channel is, of course, the Higgs to 4 leptons. And as you can see that even though the production of Higgs is quite high at the LHC, but because of the 4 lepton branching ratio, in fact, there's a significant enhancement in terms of statistics. So that's the one important thing to notice. Second channel, which bears some similarities in production with CEPC, is the ZH. But as you can imagine that for the ZH, even though the cross-section is relatively high, but because at the LHC you're dealing with very background challenged environment, either you look for Higgs to BB in the dominant decay channel, but then you suffer by systematics, or you have to look into rare decays of Higgs, but again, you suffer with the branching ratios. So I think the key message over here is that there's a significant gain in terms of statistics when you study the Higgs to ZZ interaction. All right, so in the next few slides, I will summarize some of the classical measurements, which you probably have seen in previous talks, and some of the technical details would also come in the second 2 talks. So let me begin with the recoil mass. So for example, one of the key advantages at the CEPC is you can measure precisely the recoil mass, so you don't have to really reconstruct what decay channel of a Higgs. You just tag the Z, and then you look at the rest of the events. And I just want to highlight these 2 distributions. For example, this is the classical one whenever people think about it. It's the Z to mu mu tagging. So you see the beautiful peak, and you have a slightly less sensitive channel, which is Z to EE because of the background is a bit more. But if you look at the last picture, which is looking at the Z to QQ tag, which may not be the first thing you think about, but as you can see here, that this channel doesn't really have much mass resolution. But if you look at the highlight of the results in terms of the inclusive production, you see that this channel, in fact, is the most dominant channel, which is quite interesting to learn. All right. Secondly, because we have this inclusive ZH productions, of course, then if you measure the production times the branching ratios, then you can get the unambiguous measurements of the branching ratio, of course. I just want to, again, highlight some of the main features over here by looking at subsequent decays. This slide shows you the subsequent decays involving Higgs 2 fermions. And again, you will see the fact that, for example, if you look at the Z2 mu tag, you have this fantastic peak of the Higgs. But if you look over to the other two tags, where Z goes to either hadronic decays or into the two neutrino decays, you see that they don't have impressive mass peak. But because of the enhancement in the branching ratio of the Z decays, you get significant improvement if you're looking for the overall, let's say, number of events. So this again can be highlighted over here, where you can see that this is expected precision on this quantity, and you see that the QQ bar and the neutrino decays in fact dominate the sensitivity. Right. The last slide before I move to the anomalous couplings on the Higgs to ZZ decay themselves. Given that you can extract quite a lot of information just looking at the ZH production itself, the additional power that brings in the Higgs to ZZ in terms of confirming the Higgs to ZZ interaction is much less, of course. But again, because you're looking at the branching ratio of Higgs ZZ explicitly, that allow you the absolute measurement of the branching ratios. Right, so at the CEPC white paper studies, you will see that it's looking at two different channels, looking at similar finer states. So again, this is ZH, H decays to Z star, and you're looking at 3Z in the finer states, and then you have the combinatorics. For example, you can look at the mu decays coming from this tag Z, or you can actually put in the dimuons in one of the Z coming from the Higgs decay themselves. So it's kind of a different topologies, but ended up very similar finer states. So the sensitivity that's quoted over here in the study, you can see that these two finer states involving two muons missing ET plus the two jets are quite comparable, and that's the power of the combination. In the end, you can get something like 5%. All right. Okay, so then the next half of my talk, I would focusing on the anomalous Higgs 2VV couplings. So for the obvious advantages of the CEPC, that you have a well-known square root of S and clean environment, this is really one of the best places that you can do multi-dimensional fits and really try to extract couplings or EFT structures from that. What I show you here is an approach based on scattering amplitudes. I'm aware of some of the basic pros and cons in terms of comparing this amplitudes approach with EFTs, but I would avoid this debate here. I would just present this as an alternative, just something for you to think about. And also, in fact, historically, this kind of approach has been used quite a lot in the E plus E minus B factory, so on and so forth. So with my limited theory understanding, I think there's a value in there. Okay, so assuming that this particle that we're studying has spin 0, of course, decaying into two vector bosons, one can write down the generic scattering amplitudes with minimum assumptions, let's say. So you will see that the familiar terms, which is standard model Higgs, and then the second term, the so-called G2, this is a high order term, but the spin and parity feature of this one is exactly the same as standard model, meaning that this is 0 plus. Then you have the last term, which is the 0 minus term, which is usually referred to as the CP violation components. So these are the three. As a convenient way to, let's say, to interpret the results, there's the quantity called the fraction, rather than, you might think that you want to go for exactly what these couplings are, so which is good. It's one of the ways. We introduced these sort of pseudo variable like observables such as the fraction, so you can see the definition really can be interpreted as the effective fraction of events. And this can be defined for the non-standard model or anomalous coupling components. And the one that has been tested extensively at the LHC is this FA3, which is the fraction of the CP violation component. And as you can see, the complementarities in studying Higgs-2ZZ in CPC compare with the two at the LHC. Okay, right. So most of the studies that I would tell you later is actually quite old. It was based on a SNOMAD study that we've done about 5 years ago. This is a joint adventure of several theorists and also several experimentalists. You might recognize some of the names, but quite a lot of them has worked on CMS for the Higgs-2 leptons. So what this paper is about is that we aim to provide a consistent framework or analysis tools that allow you to estimate the kind of sensitivities of extracting these anomalous couplings associated with H2-VV interaction vertex. So what I meant by consistent is that we have one single Monte Carlo that can simulate this interaction vertex for both E plus E minus and also for the PP. And we introduce the matrix element likelihood analysis, or for the LHC folks, it's sometimes referred to frequently as MELA. And this is particularly useful if we have limited statistics. It's one of the best ways to maximizing the use of kinematic information. And it's quite comparable with other, let's say, statistically or commercially tools such as boosted decision tree and so on and so forth. And also in this study, we wanted to use a consistent statistical approach to compare the sensitivity so that when you're talking about sensitivity of a quantity, there's no ambiguity how to translate the two. And some of these tools, as I mentioned, have been adopted at the LHC, especially in CMS. So this is just a highlight of the generator themselves. So I'll just leave you later to look at it. So this is a very flexible, small scale of Monte Carlos, nothing to the extent of, say, MatGraph or Sharper whatsoever. So this is really a small scale, let's say, production, mainly developed by the people who used to work at Johns Hopkins University. As a side, this generator itself was specialized, really looking into spin and CP quantities of resonances. Doesn't matter which mass it is, but mainly focusing on a resonance to two vector bosons. Right. Now, let me just go into a bit more details on this. So I show you this general scattering amplitude. So this is a theory things that we want to extract to. But then the question now we ask ourselves is how do you translate all these couplings, G's, into something that we can experiment and measure? But this has been frequently done at the Collider physics, and let's say the bridge is what we refer to as a helicity amplitude. Basically, if you look at spin zero decaying to two vector bosons, and you can write down the helicity amplitudes as 0, 0, plus, plus, minus, minus, and really these helicity amplitudes, which I'll show you later, that connects with the angular information. So you can see that the translation from, first of all, the general scattering amplitudes into helicity amplitudes, you can see that from these, let's say, G1, G2, G3, and so on and so forth, you can predict these A00, plus, plus, minus, minuses. And as you see over here, that these helicity amplitudes exactly are hidden in the angular PDFs. So now this allows me to introduce the kinematics involved with this process. So kinetically speaking, at the rest frame of the Z star, which produces the 2ZH, there are 5 angles that can be used fully. Theta 1, theta 2, phi, and so on and so forth. This is exactly the same principle as you would look at the Higgs-2ZZ decays at the LHC, exactly the same equivalent definitions. Now that we are restricting ourselves to spin zero boson into 2Bs, then this dependence of theta star is trivial because it's flat. so we cannot take that out. So eventually, we reduce it into 3 angles, theta 1, theta 2, and phi, and those can be calculated based on the form momenta of the Higgs. So it's the whole form momentum of Higgs, doesn't have to know about the decay products. The decay p-force, and also you want to know the p4 for the 2 leptons coming from the Z decays. Then what I like about this approach is that it kind of is a bit old-fashioned way, because if you look at this, you can analytically predict the distribution. So you don't need numerical methods, it's analytically predicted. And these information, I think it's quite useful as a, let's say, independent approach compared with most of the numerical methods based analysis. Just to give you an idea of how these distributions will look like, I will show you 4 different scenarios. One of them 0+, which is a standard model, and it's a pure 0-, and also you get the 2 sort of mixtures, but with different phases. So what I want to highlight in one of these distributions is that, first of all, you see that different colors really look different, of course, because of the angular distribution, because of the theory that's behind. Another thing that I would like to draw your attention is that if you look at this curve, the dots are from the numerical Monte Carlo generation, and the lines are obtained by this analytical approach that I mentioned. But of course, this is not a full validation, because you've seen only the one-dimensional projections. The underlying correlations, etc., it's not fully validated here. But I can chat with you later on the approaches that we validate the numerical aspect, the whole full 3-dimensional aspect. All right. Okay, so one of the beauty of the of E+ E- collide is that the detector acceptance, in fact, are quite easy to model with simple cuts on the leptons, etc. In fact, these can even be done numerically with some analytical with some empirical functions, which is not that hard to do. All right. With the last few minutes, I would just give you an idea of a proof of principle analysis. It should be taken with really a grain of salt, because a lot of these studies were done with back-of-envelope estimations of the events and truth quantities. So the thing that when we did this, we're aiming for order of magnitude estimation, not meant to be good within, say, 20 or 50%. All right, so I'll skip all the details, but the information we start with is roughly about 8 events per inverse Fantarbond for the Higgs ZH to 2 lepton 2b, and then we assume about 10% background. Okay, so how do we do that? So what we do is referred to as the multi-dimensional likelihood fits, which has been done, as I said earlier, in a lot of E+ E- B factories. So basically, you write down your PDF, and then you write down the information that you want, for example, the parameter of interest, FA3, and phi, and so on and so forth. The most optimal way is really to fully use the analytical power of the 3D distributions. But as I said, it can be a bit challenging with limited steps and also background parameterizations, multi-dimensions, not that trivial, which is make it less ideal at the LHC, but makes it optimal at the E+ E-. I'll probably leave you to look at this later, but I just wanted to highlight the procedure. So basically, what we did is that we tried to estimate the so-called discovery potential of these fractions that are defined. So how do we do that? So we consider that discovery is the minimum value that you can extract later with about 3 sigma precision. So basically, for each of the value that we test, we generate pseudo data sets. We generate about 1,000 of those. And then for each of the data sets, we perform maximum likelihood, and you look at what's the fit value. And we plot it in the end, the distribution, as you can see, of these 1,000 toy data set. And you look at the spread of the fit value, and that's what we call as an uncertainty. And you look at the minimum value, which can give you 3 sigma. So that's what we call it. It's consistent definitions in our comparisons. This is the figure of merit that we're after. So these plots shows you what kind of precision, let's say, we get in this CP violation component and also high order component. So you can see it's about 7 per mil and then about 2%. We can also do a extract multi-dimensional parameters of interest simultaneously, so such as these contour plots that we can do between these two. So I just want to highlight, again, the kind of results we get. What we find is that for the CP violation component, the gain in CPC is not that fantastic. It's about a factor of 3. But if you look at the high luminosity LHC, I want to highlight that actually this sensitivity is not coming from Higgs to ZZ decays, but it's coming from the VBF and ZH productions. ZZ, in fact, the decay itself has very limited power. And this is because of the cross-sections for all of these anomalous coupling components really scales up if the MZ star is very large. Okay, and the FA2, which is the high order component, CPC exhibits about 2 orders of magnitude improvement. Okay, so just to summarize, I give you a highlight of the measurements for using ZH, and I just wanted to emphasize again that in fact the leading, aside from the Higgs mass measurement, all the cross-section measurements are actually are driven by those non-classic tag channels. In fact, the QQs and the missing ETs, they are the drivers of the sensitivity now. I briefly introduce you proof of principle measurements for the anomalous couplings, and I will be very happy if, to update this into the realistic simulations and see more properly what kind of analysis we could do. All right, so thanks.
Thanks, Yanyan. Any questions, comments? Okay.
Thank you. When you consider a channel like mu plus mu minus for the Z and BB bar for the H, for example, did you consider the background for that channel?
Yeah,
I mean, the various ZZ, gamma Z, because the background, if you don't put any cuts, for example, on the BB bar, it could be a factor 5 larger than your signal.
I believe that for these studies, for the standard model type of calculations, yes, all of these acceptance and object selections, etc., were considered. They may not be to the 20% level, but I think within that kind of level is well understood. For the second analysis that I mentioned, this is a main caveat. We had some basic selections, but the background approach is quite simplified. And this is something that I'm interested to bring up exactly what, along that line.
Okay. And of course, the question of ISR corrections.
Yeah, exactly. But the thing about because for the second part, what we are mainly after is the angular informations between those two. So the sensitivity that we naively, without doing the full analysis myself, would be relatively less because we're not after an absolute measurement of the process. We're actually trying to distinguish between two different hypotheses. There, the background contribution, etc., it's a bit less because it comes in just as a statistics.
Okay, any other questions, comments?
Just to understand well, so basically you have your precision for all the different channels, right?
That's right.
And then, so I'm wondering, how did you consider the systematics and performance of the missing ET measurements and the background extrapolation due to the Z2 nu for these? Is it considered the same, or is it depending on the channel you are con?
I'm afraid I don't have a detailed answer to that, as I did not do the studies. Yachun probably can give you more, at least, points of context to answer your specific questions.
So can you repeat the question again?
No, just from the LHT experience, we know that actually the vicinity behavior and systematics and so on depend on the final state you are considering. So my point, if you have actually the same picture for all the Higgs decay channels, considering the vicinity performance, or you actually manage to introduce some variations depending on the final state you are considering.
Yeah. Here, I think vicinity is not as complicated as AHC. It's much easier for you to handle.
But
yeah.
still, I mean, it's not going to be exactly the same behavior, the same systematic,
You have,
depending on the final state.
AHC, you have a lot of jet activities, all this pile up stuff together, and these things. But here, yeah, it's much simpler, and even it's difficult. You can use also Coleman mass to have some constraint, some calibration of this. That will be situation. I would say it would be much better, than AHC. AHC, that's a trouble for us, right?
Yeah,
No, I mean, it's much simpler, but I mean...
Yeah. If we go to the real life, we still need to consider this carefully. Yeah, I agree.
I think it's a good point to raise for this white paper. We should clarify what kind of objects performances that it's been wanting to in various channels. Yeah. Yes.
I assume for the final likelihood amplitude fit, you determine all of the background parameters indeed from the data, right, using sidebands events or combined fit to that. Has this been done already, or?
No, this is a very simplistic thing. We actually just use the ZZ 2 lepton 2B as a way to parameterize the shape. That's done from Monte Carlo, so that's a three-dimensional distribution from Monte Carlo. But because in the at the plus minus you have ESSA with you under the peak about factor 10, so the specific treatment of the background is not let's say if you're off a little bit, it's not a major concern.
Other questions, comments?
On the page 15, I saw you talk about the challenge, detection response, and the background.
Yeah.
In current analysis, the efficiency correction was taken into account?
So acceptance is considered, but object efficiency, I believe for the leptons we assume about 80% per lepton or something, like that scale. But for the B-tagging, I can't remember off the top of my head. But because the selections that we use are incredibly simple, it's just lepton, PT, and eta. This allows us to parameterize these acceptance analytically.
Another question on the fit procedure.
Yeah.
Did you validate your fit procedure to see that there's any bias on the input parameters?
Exactly. So I think there are two ways that we evaluate this. The prerequisite is to look at this pool distribution, which is defined as the fit minus the input divided by the uncertainty, and we make sure that out of those 1,000, let's say you have over 90% have if you look at the ones, you should fairly consistent with Gaussian 0 and 1, so that's how we do it. And you can see here that in terms of biases that's considered, so for these ones, this is the generated value of 0.07. Well, I can't see it correctly, but the bias is very negligible.
Yeah, okay. For your this sample, is that do you think it's easier to have some interface with like CPC, the Monte Carlo tools to have some more or less like a more sophisticated study, like for simulation of these things?
We can chat it afterwards. So the generator itself, first order give you the Lazouche files, and then you can do whatever you want afterwards. But I'm not sure how CPC currently handles that.
Okay, yes, can do it, offline. Any other question, comments? If not, then let's thank Yanyan again.